This course has been a big mix of a lot of associated ideas, from algebra, trigonometry, even some arithmetic. But the thread which has held most of it together is the idea of a function. So remember, a function is something which takes in a value and spits out a value. So we eat an element of a set called the domain, and returns an element of a set called the codomain. And the set of the codomain, which are the values which actually do come out, is called the range. So we have the domain goes in, an element from the domain goes into F, and out pops an element of the codomain, specifically an element of the range. So for example, let's take a look at an idea of a function that we're used to dealing with in this course, f of x equals x squared. A real number comes in, and a non-negative real number goes out. The codomain and the domain are both real numbers, but the actual range is the set of values which can come out, or which is everything at least as big as 0. And we can draw a graph of f. And you can see the domain is f because at every x value, there's a piece of the curve. And you can see the range is the set of values that are at least as big as 0, because that's where the graph is. It goes down to 0, and you see part of the curve at every point positive. And we've talked about a large collection of different kinds of functions in this course. We've talked about power functions. F of x equals x to some power. So a is just some constant. For example, f of x equals x squared. Perfectly nice power function. Or g of x equals the square root of x, which is x to the 1/2. Perfectly nice power function. Or h of x equals 1 over x, which is x to the -1, a perfectly nice power function. So we spent a lot of time talking about power functions. We talked about polynomials, which is what you get when you take constants and power functions and stick them all together, using plus, minus, and times. So polynomials, for example, f of x equals x squared minus 3x plus 5. Perfectly nice second degree polynomial. You know right away that the shape of this is a parabola. You know right away that this parabola is right side up. We can have polynomials of higher degree. G of x equals, let's say, minus x to the 4th plus 3x cubed plus 2x squared plus x minus 5. Perfectly nice 4th degree polynomial. Looking at this, you can see right away that it goes down to the right on the end, and it goes, we know that even degree polynomials either go down in both directions or up in both directions. Since it's going down to the right, it's going down to the left. You don't know exactly how many turnarounds it has, but you do know that since this is a 4th degree polynomial, it has an odd number of turnarounds. I'm not trying to review everything in the course. That would be impossible in a short video. I'm just trying to review some of the basic kinds of functions that we've talked about. We've also talked about rational functions. A rational function, as you know, is a polynomial divided by a polynomial. So g and h are polynomials. For example, f of x equals, let's say, x over x squared minus 1. Now, there are a lot of things about this polynomial that we can't answer at this point, but there are a lot of things that we can. We could figure out that this thing has vertical asymptotes wherever the bottom is equal to 0. So it has vertical asymptotes at x equals 1 and x equals minus 1. That's where the bottom equals 0. We would set it equal to 0 and solve, and we get x equals 1 and x equals minus 1. We could see that this thing has a horizontal asymptote at x equals 0. Sorry, at y equals 0, I should say, on the x-axis, because the degree of the numerator is smaller than the degree of the denominator. That's one thing that we know. We could figure out that it crosses the x-axis at 0, and that's where it crosses the y-axis too. As to what this thing looks like, as to what the graph looks like, we're not really in a position to know yet. But if you want, I can sketch it for you right now. Let's see, this thing looks like this, and it looks like this, and like this. Yeah, that looks about right. We have no way of knowing the general shape of that curve yet. We could figure out where it was above the x-axis and below the x-axis by figuring out where this thing was positive and negative. But in terms of the general curving of this thing, we're not really in a position to be able to do that yet, unless we want to plot a lot of points until we can see exactly what this curve looks like, or approximately what this curve looks like. But there's a lot we don't know about things like this. We don't know where it's going uphill, where it's going downhill, where it's curving downwards, like it's curving downwards here. This is shaped like a hill, but it's curving upwards here. This part's shaped like a valley. This is all the purview of calculus. But we have talked about rational functions. We've talked about exponential functions. Something like f of x equals 2 to the x. You know what the graph of that looks like. Crosses the y-axis at 1, approaches the x-axis asymptotically to the left, and grows very rapidly on the right. If I gave you something like g of x equals 1/2 to the x, you know that this went downhill. So we know about exponential functions. We also know a lot about trigonometric functions. So, for instance, f of x equals sine x, or g of x equals cos x, or h of x equals tan x. We know what those curves look like. We know with sine and cosine, we could talk not only about the period, we could also talk about the amplitude. We know that amplitude doesn't make so much sense, unless you want to say it's infinity, when we talk about tangent, but we can talk about the period. We know that these two repeat every 2 pi, this one repeats every pi. We can take all sorts of functions that we've seen, we can transform them, we can stretch them, we can compress them, we can reflect them over one of the axes, we can go ahead and shift them around in all sorts of different ways, and we can take these functions that we've started with, and build all sorts of complicated functions to describe any kind of phenomenon we want. If we want to take the function x squared and add it to sine x, we can do that. If we want to take these two and multiply them together, we can do that to build a function that doesn't fit into any of our categories so far. Now, for all of these things, and even for functions as simple as polynomials, we still don't know a lot about how to tell where a function is going uphill, where it's going downhill, whether it's curving upwards, whether it's curving downwards. These are all the purview of calculus. When we talk about a function describing the position of something, if we want to take that position function and figure out what the velocity or the acceleration of the object we're describing is, we don't know how to do that. That's all the purview of calculus. And should it be important to us to find the area underneath some curve? We don't know how to do that. We also don't know why that might be an important thing to do, but that's coming up too. These are all the purview of calculus. So we have built in this course a library of functions that you can take and make bigger and bigger and bigger by combining these functions in any way you want. But to answer specific questions about how these functions are shaped and how they might relate to real-world activities, we need another course coming up called Calculus. Been a pleasure.